Good morning. I'm glad to welcome you in this university in Tbilisi, of course, in Georgia. 6 years ago, we with Rostislav Yavorsky, Iosif Itkin, and Professor Viktor Zakharov organized first conference named TMPA, and 6 years ago, and after 6 years, this conference moved outside of Russia. It's a very good point, I think, and now our conference is really international. My talk will be devoted to a specification of program libraries, and a couple of words about me. Who am I? My name is Vladimir Itsykson. I am from Russia, St. Petersburg, Polytechnic University, and now I am director of Higher School of Intellectual Systems, Supercomputer Technologies, and also I am head of a joint research laboratory with JetBrains company named Verification and Program Analysis. Main subject of my talk is software library and formal specification of software library. During presentation, we will discuss several terms. They are depicted on this slide. We will discuss a problem which using external libraries. I will describe our approach to cope with some problems with external library. Also, I will present formalism for describing structure and behavior of program libraries, our DSL for expressing a library specification, and also we will discuss several applications of our approach to software engineering. Short outline of my talk in these slides. Introductions, it's just now, and after that we discuss problems with library. Several words about our formalism for create specifications and our language, library specification language, LibSL, and 5 applications. Porting software, enhancement of static analysis, using our approach to use our language, library written in one language from another language, using our approach to detect integration error, and some words about creating specification, how we can mining specification from existing software project. And we will start with problems with external libraries. Almost any software project now consists from several components. It may be components which provide some commercial producer of this library. It may be some open source libraries, maybe architecture of your application use several components, like as example, microservice architecture and so on. And it's normal practice that your application consists from several components, several libraries, some of them produced of third-party vendors. And unfortunately, current practice of distribution libraries is very bad. Some authors distribute library as is, without any documentation. Some authors distribute libraries only with small informal documentation. Sometimes we can see some examples of library usage. And if after try to document his library, they use some technologies like JavaDoc, and as a result, we have a short description of data types and API function calls. All of libraries, unfortunately, have no formal descriptions. There are no formal rules how we must use some external library provided by some producer. And the result of lack of formal rules, it's many integration error. We face up with error when we try to use some application, when we run some program, sometimes commercial programs. And I will show a very trivial example. It's an example from the IOH to illustrate what problem I'm in. It's a very simple example. We work with file library, and we can see that someone open file. After that, he read from this file and close this file descriptor at the end of the program. It's a good program. This program syntactically correct, I hope, and this program semantically correct. But in other case, we can write such program. It's a very stupid program, but we can do it. First we close file descriptor, after that we read from them, and after that we try to open this file. It's a very stupid program, but it's absolutely syntactically correct. But it's incorrect semantically. We understand that we cannot read from closed file descriptor. Okay, how we can recognize such type of errors? How we can recognize that at first, oh, I'm sorry. At first we should, I try to use mouse. No, it doesn't work. We should know information about that at first we should open file, then read, and after that close. There are no such information in library, and we can get this information only from informal documentation of this library or from own experience. Oh, thank you. Very good. Thank you very much. My presentation will be devoted to our approach to found such current integration error and to our formal approach consists of formalism and DSL to cope with this problem. And we will start with formalism for describing specification and library. Oops. Unfortunately, there are no slides. I'm sorry. It was joke. What is main goal of formalism. We want to make our formalism as simple as possible. Why we want to simple formalism? Simple formalism use simple models, and simple models, we can analyze simple models like models based on finite state machines. If our models will very complex and it will be equivalent to Turing full models, it's will impossible to analyze this model. And we want to make formalism as simple as possible. But we want to make formalism enough powerful to express any or almost any libraries in the world. It's too difficult task, and we try to solve it. The main idea of our approach is to specify only visible behavior of program libraries and hide unsignificant details that inside of library implementation. And because we skip some insignificant details, our specification is partial specification. Our specification should describe components of program, its data types, its variables and objects from libraries, and function of library public API. Data types, variables, and function is static semantics of library. Also, we should to describe dynamic semantics of library. Dynamic semantics consists of semantics of API functions, behavior of API functions, side effects, contracts of API functions, and the main part of formalism is rules of library use. As a result, library is a composition of extended finite state machines. Each finite state machines or automaton describe behavior of only one library objects, like descriptors, like sockets, like semaphores, and many other objects. Status of automaton corresponds to object states. Transition corresponds to call of API functions. And when we need to create new automaton, it's side effect, side action of API function call. And each function consists of function signature, function contract, if we have function contract, and high-level behavior. Also, we introduce special elements of model. It's semantic actions. It's part of semantic domain of program library. More detail, you can see our approach in our publication of December of 2017. Next several slides will be very boring because they consist of some formulas. It's our formal specification of library function. Each function is a tuple of name, formal arguments, results, also precondition and postconditions of function, and also A, it's a set of semantic actions that will form semantic domains, and D, it's a set of child automata that launched during execution main automata. And set of API specification, it's named F. Second part of our specification is a specification of automata. Each automata describes with this big tuple Q, it's a set of automate states. Q0, it's a set of initial states. X, set of finished states. Finished states of automata, it states when automata will be destroyed. We use extended finished state machine, and V is set of internal variables of automat. And also we have several components. C is set of a function calls acting stimuli of automata, and C, A, and CG, it's semantic action initiated by function launch, and a set of external state machine launched by functions. And the last slide of our formal description, it's B. It's a set of any automats of library. L, it's a main automaton. It's describe behavior of entire library, and S1 and Sn is a child automat created during library execution. And the result, lib, it's tuple of F and B. F is set of library function, and B, behavioral description of library. I think it was very boring, and I tried to show it on the picture. On this picture, you can see example of our model. It's a TCP server, TCP socket, server side of TCP socket. This model consists of 3 automata. First automat L, it's a primitive automat of state of library. Each automaton has only one stage initialized. Second automat, its automaton correspond to TCP/IP listen socket. When we program TCP server, we should move one automat in listening state, and after that, he can receive requests from client, and he create one new automaton for each connection. And third automaton, it's automaton for work with each client. This is states of automaton. On the you can see some parts of API, bind, accept, shut down, and so on. It's API of TCP socket library. This type of transition, it's a creation of new automaton as a side effect of some API function. In this case, of its side effect of API function socket, and accept as example here. And red one, it's a finished state. After finished state, automata will destroy it. And a similar example of client side of TCP socket. It's more simple automata. We have 2 automaton. First one, library automaton, and second one, it's a client TCP socket. When we create socket, after that we move it in bound state by API call bind, and after that move it in established state by connect, and it's a work state of automaton when client and server can change of data.
Just one question. So you model the call stack as a sequence of automata, right, which are created and then destroyed?
It may be called a stack if a library can can create stack at automaton. Some libraries don't create dynamically automaton. In this case, yes, we can stack main automaton, one automaton of listen socket, and many automaton of work socket.
So if it's recursive call, then you will have points on the same automaton, right?
Yes, but really in automaton, one automat cannot produce recursive other automaton in a real situation. But maybe you can create such library, but it's an unreal case. Okay. Now we will discuss our language. We develop a special language, LibSL, library specification language. It's a user-friendly way to create such specification. Our language allows defining library name, semantic data types, any automata that includes in library, global object, global variables for functioning library, and description of API functions. Structure of specification and LibSL language depicted on this slide. First line is name of library. Second section, it's an import section. We can import any LibSL description to build complex LibSL descriptions. Section of semantic types, it's a special section when we can define types used in the library and define semantic aspects of types. I will discuss about semantic types later. Automata section consists of description of each automata from this library. Function section describe API of each function from public API of library, and set of global object and global variables that can be created when library running. Okay, now we will discuss more detail. Section of semantic types. Semantic types, it's extraction of classical types. And you can see some aspects. This part, it's just alias definition for standard types. These types is predefined types of our language, and these types, it's types from programming language. You can use names of your programming language because our LibSL language can be used with any programming language. Second part, it's semantic type definitions. What is semantic type? Right side, int, void, and so on. It's a classical types of programming language. But left side, it's annotated type. Annotated type add special semantics to source type, and this semantics used when we solve some application tasks like porting libraries porting application from use one library to another. And these semantic types can add special semantic to arguments of formal arguments of library AP functions. And second types of semantic types not only annotate types, but also annotate value of types of concrete type of programming language. It also helps us to migrate from one library to another library when they use several interpretation of types. Next section of our language is Automaton description. In this slide you can see Automaton BSD circuit, internal variables of Automaton, state of Automaton. In this Automaton you can see 5 states. 4 states is simple states and 1 finished states. In finished states, that name closed Automaton will be destroyed. And moving from one state to other states, as example, this line means that we can move from state created to state bound by means of API call bind. This is a list of API call of our library. Second section, section of our language is API function description. You can see example of description of 3 functions: function socket, accept, and send. Each function use semantic types, which we will describe before. We can describe a creation of new automaton by this syntax. We have a special annotated variable which point to a variable that consists exemplar item of automat. And when we work with accept, send, its action performed on this automaton. And 2 types of semantic action. Semantic action, it's adding of external semantics to behavior of this function. You can see that function send have 2 semantic action. If len more than 0, it's action send, and it's normal behavior of function. And if in another case, a semantic action error, and this semantic action can help us to detect library errors during analysis. And last one section, it's global object sections. We can declare and define variables and declare exemplars of automaton. In this example, we create 3 predefined automaton for std_ir library, std_in, std_r, and std_out. It's 3 description descriptors of 3 stream: input stream, output stream, and error streams. It was a short description of our language, and now we can move to applications of our approach. We will discuss 5 applications of our approach, and first one is supporting of software. When we need porting software, we sometimes we have a fully tested application that use some library. But sometimes we want to change this library and move our application from using one library to another one library. And both libraries have similar functionality. Maybe first library use its file library, and second library is stream library. And we have this situation, and we want to move from use old library to use new one library. And first application is to automation this procedure to migrate from old to new one library. When we where we need to migrate to new library, there are several situations. First one, when we need to migrate to new operation system, as example from Windows application to Linux application. Also, we want to move our application from one platform to another one. As example, to a mobile platform to Android. Next situation, when we have some library and producer of this library upgrade it and produce new version of this library, and we need to move our application to use a new library, and it's very frequent task. Also, we want to move to similar library, but a library with another functionality. Maybe its first library was unsafe, and next one is safe library, and we need to move from unsafe to safe one, and so on. As how solved this problem in program in software industry. Some use cross-platform libraries, some try to move some intermediate layers which can work with old and with new libraries. But it's a particular decision, and really almost always we manually rewriting any function calls in our application from using old library to using new library. Which problems? Problems, it's a lot of manual actions, and sometimes we must change several thousand lines code of our application. But in fact, we have before well-tested and well-verified application. And after move to new library, we create a new program. And all our efforts of testing this application is made in vain, because we have new application and we must retesting it or verification it. And our approach is to automate the program transformation from old to a new library. And our general algorithms is following. We create a specification of the old library by using LibSL language. We create specification of new one library. After that, we implement algorithm that checking compatibility between old library and new library. And if new and old library are compatible, then we build model of source program, model of bus libraries, and we implement algorithm to translate model of old source program to new one, and after then generate source code of new program. You can see on this picture, it's a source code of source program, two specification on source library, specification on target library. By library model builder, we built two models. By program model builder, we built a model of our program. And model converter convert source program model by using two models to modified program model, and after that we produce new source code of target program. And main point of our approach is that the new program should be correct and should be as correct as was correct previous program. As a result, we created two tools. One important tool for C program language, it's first experiment tool, and second one more functional tool for Java program. And now we can migrate not any but functional program from in Java language, and we successfully ported several Java program found in open source repository in internet, and this migration was successful. Some detail you can see in two our articles on this subject. Second application of our approach is enhancement of static analysis of program. The main program of static analysis, it's we need to inter-procedure analysis, and when we try use static analysis of a big program, we have increasing the analysis complexity because we need to use several components, several libraries, and a model of a program of static analysis, and very, very big. And as a result, increasing analysis is very complexity of analysis increasing, soundness and precision of analysis, unfortunately, is decreasing because we need some approximation of external components. And main idea of our approach is to use our partial specification to enhance static analysis. We use LibSL specification instead of source code of analyzing libraries, and respectively a model of our libraries is replaced of models of external components or external libraries. And this approach was realized in our static analyzer called BMC, called Borealis. Borealis is BMC static analyzer. BMC, it's bound model checking, is based on classical approach bound model checking. Source code of program converts to logical predicates. Correctness rule also converts to logical predicates, and function summary includes in resulting predicate. In big predicate, it can consist in thousands and millions of elementary predicates. It's an input of SMT solver. We use Z3 or Bolector solvers, and after that we get a result of solver and interpreted it and found program bugs. And scheme of approach you can see on the slides. We convert source code by LLVM tool to LLVM intermediate representation. After that, we extract predicate from LLVM. This predicate extraction, it's a special representation called predicate states. We enriched these predicate states by assertions and by function summaries. And after that, this state converts to SMT formula. SMT formula moved to input of SMT solver, and we have two results. if it's unsatisfied, it's okay, or if it's satisfied, we can counter example and can decide what reason of error. And two components, this one, it's enhancement of standard approach. We include our LibSL specification as a function summaries in this toolchain and enrich by our specification this big predicate collected from program, from assertion, and from function summaries. And as a result, we can analyze program with using of external libraries when we don't have source code of these libraries. How it works? It's small example of a description of behavior of library function. It's a rec function from socket library, and this is a function. This is behavior of function, and action, semantic action, help us to detect errors inside of libraries. This example of actions and this type of action, and this string is diagnostic message for this error that found in this function. That's all about this application, and now we move to next application of our okay, I try to next application of our approach is cross-language integration. The goal of this application is to try use library from one programming languages from another programming languages. There are several standard approach to solving these tasks. It's remote procedure calls and FFI, foreign function interface. But both of standard approach have some problems because we need to write many of manual source code for integrate library in written in one language to application written in another language. And the main idea of our approach is to use LibSL specification to automatically generate wrappers for library function and receiving part of library function. Scheme of this approach depicted on this slide. We have main program, we have library, we have LibSL description of library, and we create a wrapper and receiver for each language, not for each library, only each language. And by means of code generator, we generate wrapper and receiver for connect first language and second language. And by RPC mechanism, we communicate main program to library, and main program and library are written in absolutely different program languages. We automatically generate this linking model. We release some tricks to cope with serialization and so on. And as a result, we can see in this table, it's two standard approach based on RPC, FFI, and our approach called library ring. wrapper and receivers, in our case, generated from interface description, not manually as in alternative approach. We need create wrapper core only one for language, but as example for FFI, we need create this for pair of language. In this case n, and this case square of n. Also, several another advantages of using automatically generated code. We implemented it as our project library ring. At current, we can written libraries in C, Python, and Golang, and wrappers can be made for Java, Kotlin, and other Golang. We test our project on several popular libraries. Also, we have several tests for benchmark our approach. This is a small example of how we describe of Z3 libraries. It's Z3 Automaton, and this is Z3 API. And next slide, you can see example of Kotlin language that use the three library. And before our approach, it was impossible to use these three libraries in Kotlin language. This approach, more detail, you can see on our poster section. My young colleague Artem Aleksiuk on poster section will describe this approach in details. One more application of our approach is integration error detection. We try to detect when main application use some library in incorrect way. And my idea of this project is use dynamic analysis of application to check correctness of library usage protocol. During dynamic analysis, we record program trace and check their correspondence to our reference behavior, which set by LibSL specification. We use specification-driven instrumentation. After that, we execute program and collect trace. We execute our program on special test, and after that, we logging any API function and any context. Collected trace, after that mapped on our model, and we check correctness by check preconditions, postcondition, and validity of Automaton state change. This short scheme of our approach: source program, instrumented by LibSL description specification, instrumental program execute. Several times we get traces, and each trace we check trace of correctness by reference model. And after that, we create reports. It's a very small example of this approach. It's our model of our library of TCP client. In this moment, you can see state of library. And this is an example of trace. If we use socket call, then we produce new Automaton. After bind, we change state of Automaton from created to bound. And in trace, it's error. We use rec call, but it's not possible in this state. and our system detect this situation and detect error because you should use connect, and after that use rec call. And the last one of our application is specification mining. The main question is where can we get specification? Where can we receive specification for external library? Of course, the author will not provide specification to their libraries, unfortunately. The programmers can create specification because they have lack of knowledge about libraries. And the reasonable way is used to knowledge of programming community. There are billions of open source projects. There are millions of projects that use target library. And our approach is to extract library specification above mean of learning of project from open source repository. And approach depicted on this slide. We find a project from GitHub which is written in Java and use our target library, loading project to local disk, and generate tests if there are no tests for this project, running tests, collecting project trace, and analyzing any trace for one library to generate predicates, and these predicates convert to predication skeleton. And after that, programming can enrich skeleton by some element of specification. This approach you can see also on our poster session. Our young colleague Inga Yegorova will describe it in detail 2 hours later. Okay, and conclusion. What's about application and what else? In which areas we can also use formal specification? There are 3 directions of extending our methods. It's a static analysis for library violation detection. In our previous approach, we used dynamic analysis. Of course, we can use static analysis for it. We can also use static analysis to mining specification. And one more way, it's automatic creation of library documentation based on formal specification of libraries. That's all. It's conclusion. Thank you very much. I'm sorry that you must suffer from my English. I'm sorry, but that's all. Thank you.